In this video lecture, we will explore the 8085 microprocessor programming technique for adding to 16-bit numbers and storing the resulting sum, including the carry, in consecutive memory locations. Manually input to 16-bit numbers into designated memory locations. The first number should be placed at addresses E000 hex and E001 hex, while the second number occupies E002 hex and E003 hex. After execution, the resulting sum is stored at locations E004 hex and E005 hex, with the carry saved at E006 hex. The accompanying diagram illustrates arbitrary data for reference. Different values are used later in the video to clarify the explanation. Let us now examine the step-by-step approach for developing the assembly language program that performs the addition of to 16-bit numbers. Step 1. Store the first 16-bit number in the memory locations E000 and E001. Step 2. Store the second 16-bit number in the memory locations E002 and E003. Step 3. Initialize the register C with 00H, which will be later used to reflect the carry. Step 4. Load the HL pair directly with the first 16-bit number using LHLD instruction. Step 5. Exchange the content of HL pair with the pair using XCHG instruction. Step 6. Again, load the second 16-bit number using LHLD into HL pair directly. Step 7. Perform double addition on HL and they pair and store the content in HL. Step 8. Check for carry. If carry, then increment the content of register C by 1, else continue to save the result and the carry to memory. Step 9. Copy the content of register C to accumulator A. Step 10. Store the content of HL directly into the memory locations E004 and E005 using SHLD instruction. Step 11. Store the content of accumulator to the memory location E006 reserved for carry. Step 12. Halt the operation. Let us now summarize the algorithm as shown here. Now let's see the flowchart. Let us now write the assembly language programming for Intel 8085 microprocessor. MVIC 00 means the move immediately 00 hex data into the register C to clear it. The instruction LHLD E000 loads the HL register pair with data from two consecutive memory locations. Specifically, the content at address E000 is moved into the L register and the content at E001 is moved into the H register. XCHG is the exchange operation between HL pair and DE pair. So the contents of these registers are swapped to store the first number in DE pair register. Again using LHLD E002 instruction to load the second number into HL pair register. The instruction DADD executes a 16-bit addition operation, adding the contents of the DE register pair to the HL register pair. The result is stored in HL, and the appropriate flags are updated accordingly. To check for carry, the JNC jump if no carry instruction is used directing control to the label next at memory address F00E. If a carry is present, the jump is bypassed and the next instruction, which increments the contents of register C, is executed. Conversely, if no carry occurs, the JNC instruction is executed, causing the microprocessor to skip the increment operation and proceed directly to saving the result. Regardless of the carry status, the microprocessor stores the content of the HL register pair into memory. Using move A, see the content of register C is transferred to accumulator. The STAE006 instruction to stores the accumulator's value at memory location E006 directly. Finally, SHLD E004 stores the content of L register to memory location E004 and the content of H register to the memory location E005. Now using HLT we can halt the operation of the microprocessor Intel 8085. To conclude, this programming exercise showcases the structured method of using Intel 8085 instructions to perform a 16-bit addition with proper carry handling. By manually placing data into specific memory locations, leveraging register pairs like HL and DE, and utilizing instructions such as LHLD, DAD, JNC, INR, and STA, we achieve a complete memory-based result storage. This approach not only reinforces understanding of register operations and flag manipulation but also highlights the elegance and efficiency of 8085's instruction set in executing low-level arithmetic operations. Thank you so much for watching. Your support truly means the world to us. If you found this video helpful, consider subscribing to the channel. It's completely free and just one click goes a long way. By subscribing, you are not just staying updated with our latest technical tutorials, you are also helping us grow and continue creating even more detailed and valuable content for learners like you. Every subscriber brings us closer to making technical knowledge accessible to everyone. Don't forget to hit the bell icon so you never miss an update, and do share the video with others who might benefit. Together, let's build a thriving space for learning and innovation.